Um, uh, Hi. So today we're going to continue from last time where we were talking about higher order derivatives. Okay, so unless there's any questions, I'll just get started. Okay, here we go. All right, so I'll begin with a review of some notation, more or less, that we had last time, and then we did a few things with this notation. And so first, so we're talking about this higher order differentiability, and you'll recall the definition goes like this: that and so this is kind of a bootstrapping definition. You start with uh, class C1K, and then you do class C2, C3, and so on. Um, and so you say that you're of class C K if you're of class C1, and the derivative is of class CK minus 1, right? That's the definition of being of class CK. All right, and so then we spend some time um, developing some notation that connects this to higher order derivatives that second derivatives and third derivatives, because this definition only requires the first derivative to state the definition. All right, so here's how we did that. So we did this business where we froze some of the arguments of d phi. Okay, so d phi is a mapping, you'll remember, from O cross U into V. Okay. Um, And so we're going to freeze the u argument so that we end up with only a function of O, and the resulting thing we denote like this. All right, so u1 is the element of u that we're freezing, and then we get a function on O defined like this. Okay, and now you have a function on O, and so we know how to calculate first derivatives of those things, and so we can do that, right? So we can take this function, we can take its derivative, okay? And then we can apply this procedure again, where we um, um, take the derivative in the direction of some element of u, and that gets this symbol, and formally it looks like this. So it's a bit messy, but conceptually it's not actually that difficult. It's just you have to kind of build up the notation a little bit carefully. But the idea at every step is that you want to be stuck with differentiating functions only of O, not of O cross U or O cross U squared and so on. Okay? All right, but after you've done that, and so you can continue this process, and you have to. We don't necessarily know a priori that any of these symbols make sense, but let's suppose it all does make sense. Then we can define this thing which I call dk phi. This is the kth derivative, um, and this is the function of O, the domain of phi, k copies of u, and it's simply defined like so. Right? So we have this process that we talked about above, and I've just iterated that k times. Okay. So you differentiate with respect to x in the u1 direction, then you freeze u1. Then you take the derivative with respect to x in the u2 direction, then you freeze u1 and u2. Then you take the derivative and so on. Okay, so that's the idea. It's a simple enough idea, but it just takes some notation to make it precise. All right, then I stated and proved half of the result, that phi is of class CK if and only if dk phi, according to this, is well defined. So in other words, this business over here makes sense, and continuous. All right. So um, we proved that if phi is of class CK, then this is well defined and continuous, and we did that by induction on K. Right? The other direction, as I said last time, is genuinely hard. Okay. All right, and the proof is in the course text if you feel like taking a look at that. Okay, good. So now we have higher derivatives, so we can talk about those. All right. Um, And so we introduced this piece of notation, capital DK phi. Oh, so sorry, before I do that, I stated, but again didn't prove, um, that if you freeze x, okay, then as a function of all the u's, uh, DK phi is multilinear. Okay, so multilinear means that if I freeze each argument, sorry, if I freeze all but one argument, the resulting function is linear. Okay, so that's what multilinear means. Um, and it's symmetric, meaning that I can scramble the entries here in whatever way I want. Okay. And this corresponds to, so as I said last time, the symmetric part corresponds to the fact that in calculus that you're familiar with, that if your function is, let's say, C2, then it doesn't matter what order you compute the partial derivatives. And that's also true for higher order differentiability as well. If you're class CK, then it doesn't matter what order you compute any derivative, partial derivative um, up to order K. All right. Okay. All right. So then, now that we know that as a function of the u's, this thing is symmetric and multilinear, I can now define this mapping from O into the set of, so I introduced this notation last time. So this is the set of K multilinear. Okay. So this therefore means that it takes K copies of U and maps into V, and it's multilinear and symmetric. All right. That's what that package notation means. Okay, and it's simply, dk phi this dk phi is the same as this dk phi with x frozen. Okay, so that's right. So x here is, um, so this thing is a function of x into the set of symmetric k multilinear symmetric mappings. Okay, so I said, and I'll repeat it here, dk phi is not generally continuous. And this is one of the ways in which this theory of differentiability differs from the version of differentiability that you would have learned in multivariable calculus, because the very definition of being class CK in the classical version of multivariable calculus, the very definition is that this thing is continuous, right? So in our theory, it's not. And we talked about this in some detail for the case that k equals 1. All right, but this is true for arbitrary k. All right, so we did all that, and then the last thing we did at the end of the lecture last time was we proved what I called the composite mapping theorem. So this is like a higher order chain rule, and it just says the composition of CK mappings is CK, right? And um, that was a good proof to look at because it illustrates how you use this definition, okay? Because what we did by induction is we proved that d phi, okay, and so in that case it was d of psi composed with phi. It was the composition whose derivative we were interested in, but we had an explicit formula for that, and so we were able to prove by induction that if psi and phi are of class ck, then so is their composition. So it was a good illustration of this definition. Okay, all right, good. So carrying on. All right. There's a bunch of useful facts about higher derivatives, and we're going to talk about those. So we talked about the composite mapping theorem last time. And, if you think about it, possibly to prove the differentiability, this thing is of class CK, one way to do that maybe is to try to calculate its kth derivative, right? So what is dk of psi composed with phi? All right, so this is a bit of a handful of a thing to get your hands on. And this is known in the theory we're talking about and also in the classical theory. The formula and there's various versions of this formula, and they're all kind of called uh, the Fabre-Bruno formula. Okay. And I'm going to state the Fabre-Bruno formula, and um, the proof is not hard. I'm not going to go through it. It's really, it's more of a combinatorial statement. And I want to maybe try to sort of um, illustrate to you why this is really a combinatorial statement um, to get the explicit formula. And so maybe let me do this. So let's do something very clunky and second year undergraduate-y. Okay. Um, let's suppose we have phi mapping again like we do when we talk about this stuff, Rn into Rm. Okay, and I want to and psi mapping Rm into Rp, let's say. All right, then what is so we know. So let's think about just about Jacobians, right? So just normal Jacobians, and so you know that the chain rule formula is this. Oh, sorry. Okay, so it's d psi at phi of x composed with, all right, so this thing, um, well, this thing is uh, an M by N matrix. Okay, that's what the Jacobian is, right? That's just d psi. And then you compose it, meaning matrix multiplication, composition of linear maps, with d phi of x. Okay? So let me write this in sort of more clunky notation, just so you can see really nuts and bolts wise how this works. All right, so let me write it like this. Let me write it as d of.
I guess on the left-hand side, you also need to evaluate at a
Oh,
particular
sorry, yeah,
point.
at x. Thank you. Yep. Yeah. Okay. Okay, so I'm going to write this just the partial derivatives. Okay, and so this psi composed of phi is going to be a mapping from Rn into Rp. Okay, and so this mapping will have p components, therefore, and let me denote these by, let's say, S. Okay, all right, so, and I'm going to take derivatives with respect to Rn. Okay, so there's going to be n of those. All right, so let's say xj. Okay, and this formula simply reads like this. It reads d psi. Okay, now psi. I'm sorry, there's going to be a sum here that I'll put in. I'll give myself some space. So d, oopsie, d psi. Okay, so psi takes values in or sorry, yeah, so psi takes values in RP. So there's going to be d psi s. Okay, and then psi depends on m variables. Okay, so let me call those variables y, and this will be d y, and let's say use an index a for those. Okay. Okay, and then I have the Jacobian for phi. Okay, and so that's, and I'm leaving off. I'm going to now just make my life simpler, and I'm going to leave off these arguments here. Okay, just write the partial derivatives. All right, so it's d phi a by d x j, and here s goes from 1 to p, and j goes from 1 to n. And there's a sum, a equals 1 to m. All right, so the sum here sort of stands for the matrix multiplication that I have here. Does that make sense? Right, so I'm being very
Yes.
sloppy, not sloppy, messy, but I'm being explicit, and and I'm doing that on purpose.
Yeah, it makes sense.
Okay, good, thanks. Because now what I'm going to do is I'm going to differentiate again. Okay, so and it's just easier to do the derivatives in this form than it is to do it in this form, at least um, when you're starting out thinking about this stuff. So let's take a second derivative. D2 psi composed with phi s by dxj dxk. Right. So if everything's sufficiently differentiable, say class C2, then it doesn't matter what order you take those derivatives. Okay. So now you just differentiate the right-hand side, and you're just going to differentiate it using the chain rule again and the product rule. Okay, so let's see how you would do that. Okay, sum A equals 1 to M. All right, so now I need to differentiate this. Okay, but remember what this really stands for. This really stands for this evaluated at phi of x, right? So when I differentiate this, I'm going to use the chain rule. Okay, so it's going to be d2, it's this psi s by d y b d y a d phi b by and so here the thing when I differentiate this expression, I'm differentiating it with respect to xk. So here I get a dx. And so, sorry, there's this other part of my life where I write indices as superscripts. So, all right, and then you still have this thing. So d phi a by dxj. Okay, so that's the derivative of this thing with this fixed. And so now I'm going to take the derivative of this thing with this fixed, because that's the product rule. Okay, plus. And sorry, I need also here to sum over B, just like I summed over A here. Okay, so this is A, B going from 1 to M. All right. So then I have sum A equals 1 to M. Okay, so I'm leaving the first term fixed. And I'm differentiating the second one with respect to xk. Okay, and that's the formula for the second derivative, sort of all spelled out. Okay, good. So now you can imagine, and I'm not going to do this, but you can imagine taking the third derivative. Okay, and so what's going to happen when you take the third derivative? Well, let's maybe just talk this out. All right. So we're going to differentiate this term now, which is a product of three terms. Okay, so you're going to differentiate that. And so you're going to get a third derivative term, which looks rather like this one. Okay, except it's going to have another one of these tacked onto the end. Okay, so it's going to be a formula that looks just like this, but with a third derivative here and another d phi by dx term added in there. Okay, then you're going to fix this and differentiate that. So that's going to be a second derivative of this thing, and then a second derivative of this thing. Then you're going to fix this, and then differentiate that. And again, you're going to get a second derivative of this and a second derivative of this. Okay, and then down here, when you differentiate this, you're going to get a second derivative of this and a second derivative of this here. So what you end up getting, interestingly, is you end up getting three terms which kind of have a very similar form. They involve a second derivative of this, a second derivative of this, and then a first derivative of this. So you get three of them. Okay, and they're all basically the same. right? And so that's where and then that 3, when you continue differentiating, that 3, gets turned into a whatever 7 or something, and it becomes some horrible, nasty, ugly formula. All right, and it's really difficult to see how to combine that into a neat package. All right, and there's, like I said, there's not a unique um, combinatorial formula that you get. There's different ways of expressing that, and so I'm going to just do one. They're all equivalent, of course, because it is whatever it is, but they're just sort of different ways of expressing it. And so that's what Fadi Bruno did. Okay, good.
Just
So
a quick question.
yes, please.
So this formula, I mean, I understand that it exists and everything, but is it used for
Yeah,
anything?
yeah. So there's parts of it that are definitely used, and so we can even see that here. Okay, so if you look at these formulas for the derivative here, it's linear, for example, in the derivatives of psi. Okay, but it's not linear, for example, in the derivatives of phi. All right, and that is a fact that shows up. Um, and sometimes you don't necessarily care, and maybe we'll see some of those instances later on in the course. You don't necessarily care about the exact, the 3 that shows up in the third derivative and whatever the 7 that shows up in the fourth derivative. Um, but maybe you care about the form of what that thing looks like, and you're going to draw some conclusions based on the form of that. So that's one reason why you sometimes are interested in the formula. And also, if you're working with um, uh, mappings that are not just differentiable but are analytic, then you know then that analyticity, an analytic function is determined uniquely by its derivatives at a single point, and so then it becomes very important to understand what all those derivatives look like if you want to, for example, study compositions of analytic functions. So yeah, the answer to your question is, unfortunately, sometimes you need to know this formula.
Okay, so you don't really use it so much for computations, but you use it for qualitative
So
analysis
I would say
of.
when we're talking about just, say, infinitely differentiable or finitely differentiable things, the nature of the formula you make reference to, but the exact formula you don't. But when you're
Yeah.
working with analytic things, sometimes you need to take into account the precise formulas for these derivatives of compositions.
Okay,
Yeah.
cool. Thanks.
And we're not going to be talking about analytic things in this course, so that won't come up. Yeah, but it does come up, sadly. So I'm going to tell you what the formula is, just for fun, basically. And then you can see the combinatorial nature of it. Okay. Okay, so let's just set this up. So I'm going to sort of state the, whoops, I'll make this wait again. So by the way, can you guys see the yellow? Sometimes the yellow doesn't show up. Does the yellow show up to you guys?
It shows up for me.
Yeah, okay, all right, yeah. All right, so let's do Fadi Bruno. And so I'm just going to write it down. Proving it is not hard. Um, it's really just the proof is really combinatorial. Okay, just bookkeeping in the way that we're going to write the formula. It's really just bookkeeping partitions of sets. Okay. All right. So what's the setup for Fadi Bruno? So U and V are LCSs. O in U is open, and phi. Oh, sorry. I'm doing compositions here. So W, and here I need an N, and um, and an O. All right. Then I'm going to take phi in CK of N, psi in CK O, and phi of n is contained in O, so I can make the composition. All right, so that's the setup for Fodder-Bruno. It's the same as the setup for the higher order chain rule that I did last time. All right. So you need to introduce some, like I said, this is really combinatorial, so has to be something combinatorial here. And as I said, there's multiple ways of doing this. We're going to work with partitions of sets. Okay, so let P, K, J be the set of partitions of the set with K elements into J distinct subsets, distinct non-empty subsets. Okay. And, so for example, P 2, 1 is okay. And I'll let you write down some other versions of that. Okay. Now the actual number of elements in PKJ, there's not some nice factorial formula for that. It is whatever it is. Okay. All right. So if we take some indices, I1, let's say, up to ij in 1 up to k, and I'm going to just introduce some shorthand. We're going to abbreviate. Um, um, UI. Okay, so I here I'm going to take to be just the list I1 up to ij, and that'll simply be U I1 up to U ij. Okay, so it just saves me from having to, so if I have some right, and that's not a K, sorry, I apologize. This right here is a J. Okay. So if I just have some subset, I1 up to ij of these indices, then this just corresponds to the corresponding, some corresponding list of vectors in U. So this is in UJ. Okay, so it's just shorthand. All right, good. All right. So then we can write down the formula. And here's what it is. So D, K, psi composed with phi of X, U1 up to UK is okay, so it's maybe interesting just to take stock of these formulas that we did up here. So like I said, you see some terms that are linear in the derivatives of psi, okay? And the second derivative of the composition here involves a first derivative of psi and then also a second derivative of psi. So we're going to see something like that show up. Okay, so we're going to see a sum j equals 1 to k. Then I have this weird combinatorial sum. I'm going to sum over the partitions in pkj. Okay, so I have I1 up to ij in pkj. All right, so let's make sure we understand what these are. So pkj are the partitions of this set into J distinct, so non-intersecting, non-empty sets. And so the point is that this is a collection of indices from 1 to k. The union of I1 up to ij is the set 1 up to k, and these sets have empty intersection. Okay, does that make sense? At least, I mean, I'm not asking you to understand why this shows up in the formula, but at least what the formula means.
Yeah.
Okay. All right. So you get dj psi, okay, evaluated at phi of x, okay. All right, so again, that corresponds in our simple calculations up here to these terms, okay? So then we're going to give arguments of d psi, and these arguments of d psi are going to be various kinds of derivatives of d phi. Okay, and so it is d. Okay, so now we're going to differentiate phi a certain number of times, and the number of times is going to be the number of elements in I1. Okay, so it doesn't necessarily have to do exactly with what I1 looks like, but the number of elements in I1. So it's card. So card means cardinality, so just the size of the set. Phi of x, and then u I1. Okay. All right, so again, this notation refers to this. All right, and then you just do that for all j terms in the partition. Okay, so d card ij phi of x u I j. Right, so the formula is not so bad actually. Coming up with the, sort of deducing that that's the right formula, that's the hard part. And, typically with Fodor-Bruno, once you have a formula, it's sort of easy to prove it by induction. But finding the exact formula takes a bit of patience. Okay. And so, as I said, this is an easy inductive proof, easy inductive combinatorial proof. So it's combinatorial by induction. And full proof, and it's not even long. It's given in the notes. Okay. All right, so that's Fodor-Bruno. And so again, well, I will on occasion make reference to Fodor-Bruno when we go through certain kinds of calculations. But as Abhijit said, the precise nature of the formula won't necessarily be of importance to us, just the form of it. Okay. So other kind of technical stuff that's interesting. So maybe because it's not very hard, we'll talk about differentiability of weak integrals. So we've seen that weak integrals are actually quite important. They allow us to get access to useful relationships between a function and its first derivative. Okay. So what we want to do is we want to know if we can basically swap different derivatives and weak integrals. That's the idea. All right, so you'll recall that you have formulas like this that come from your past life. When can you differentiate under the integral sign, right? So that's sort of part of classical analysis. And so we'll see that the conditions here are really rather like the ones you already know about. Okay, so what's the setup? All right, so we have two variables that we're gonna talk about functions of two variables, one that you're integrating. Okay, so let I be an integral. Let U, V be LCSs. Let O in U be open, and let phi, okay, so phi here is going to be a function on of O and I, okay, and the idea is we're going to integrate out I, and we're going to ask that it be differentiable with respect to O. That's the idea. So O cross I into V. And then now this thing has to satisfy a bunch of conditions, and these conditions will look familiar to you from your classical analysis course. Okay, so okay, so phi is a function of these two variables, O and I. And so I'm going to be writing down partial derivatives. Okay, so I'm going to write d1 j phi. Okay, now let's make sure we understand what kind of a mapping that is. So this is the jth derivative of phi in the first direction. Okay, so that's with respect to O. Okay, so this will therefore be a mapping from O cross I cross j copies of U, because that's what the derivatives do. The jth derivative takes um, j copies of the thing I'm differentiating with respect to into j. Okay, so this mapping needs to be well-defined and continuous. So the derivatives have to exist and be continuous. All right. Okay, so the next thing is, so I'm going to be swapping derivatives and integrals. And so the next thing I'm going to ask is that the integral, and so I'm going to obviously be integrating with respect to I, okay? And I'm going to ask that that integral exist for every point in O. Okay, so the function, which I'll call psi, which is the integrated function, from O to V, find phi. Okay, psi of x is weak integral over I, phi of x and s ds is well defined. Okay, so that means for each x, the expression on the right-hand side exists, and I'm making no assertions about any properties of psi at this point, just that it's defined. Okay. Now I'm going to make some assumptions about the weak integrals, not just of phi, but of its derivatives. And so if you again think back to your classical analysis course, when you swap the derivative in the integral, you needed for the derivative for the function to be integrable and for its derivative to be integrable. Okay, so we have an analogous condition here. Okay. Okay, so this is going to be a function now of x u1 up to well, let me say j. Okay, so now it's going to be the weak integral of the jth derivative. So d1 j phi of x S U1 UJ DS. Okay. All right, so I know that this thing, whoops, I know that this thing that I'm integrating here is well-defined and continuous. All right, so the integrand here isn't too crazy. Okay, but I'm still I am assuming that its integral over I exists. Okay, and again, I'm not assuming any continuity properties of this mapping here. Okay. All right, so then all of these things being true, and so again, I think if you look back to your classical analysis course, you'll have a theorem that looks very much like this. And the conclusions are also very much like your classical analysis course. All right, so the mapping psi. Okay, so it's this mapping is of class CK, and its derivatives are the integrals of the derivatives. Okay, and okay, and and so what this formula that I'm about to write down says is it says the derivative of the integral is the integral of the derivative. Okay, so d j psi of x u1 up to uj is, and so sorry, I often forget my weak integral here, is the weak integral of the derivative, right? So this thing here is the integral function, right? And so this is saying the derivative of the integral is equal to the integral of the derivative. Okay, so whoops, d j of x s u1 uj ds. Okay, good. So the proof is by induction. I'm going to just prove the base part of the induction, the one for, it's by induction on K, and so I'm just going to prove the case when K is equal to 1, because the inductive step in the proof is exactly the same. I'll explain exactly in what way it's exactly the same. All right, so I'll just do the K equals 1 case and then talk about the rest of it, because it's really just a copy and paste with some extra arguments. Okay, so we'll do the case. K equals 1. All right, and so I need to prove that psi is C1 and that its derivative is given by that. All right, so I write down the difference quotient. Okay, so psi of x plus tu minus psi of u over t. Okay, so by definition, this is the weak integral of phi of x plus tu s minus phi of x s over t ds. Okay, and you do the thing that we always seem to end up doing when we have expressions like this. That is, we use the mean value theorem, okay? And we use the mean value theorem for S fixed, okay? And for a curve, the straight line path that goes from X to x plus tu. Okay, so there's a little step that I've left off here that often gets left off, and that is you're going to work in a small enough neighborhood, all right? So small enough t's so that the straight line path from x to x plus u or x plus tu remains inside O. Okay, and you can always do that because O is open. So if you make t small enough, you can be sure that that straight line path remains inside O. Okay, so I'm leaving off that little tidbit. Okay, all right. So weak integral I. So now we're going to use the mean value theorem. So we're going to have two weak integrals. Integral from 0 to 1. Okay. Okay, so it's phi of x plus r. So r is going to be the integration variable. Sorry, it's mean value theorem. So it's derivative of phi. D 1 phi, so d phi of. So it's x plus r t u s ds. Okay. Sorry, I go dr first. Dr ds. All right. And I still have the 1 over t. I'm sorry, the 1 over t. Okay. And so now there's this thing that you do in these situations. And I'm sorry, that's not an S there. That one is a U. Okay. Sorry, it's not a U. So it's a TU because I'm going from X to TU. Okay, so here I'm going to get a TU. All right, good. I think that's right. Okay, what's the next step? So this is a thing that we've repeated a few times, and so I'm quizzing you to see if you were paying attention. So the whole point of what you do with these mean value theorem computations is you take this expression, which has a t in the denominator, and you rewrite it as something that's well defined at t equals 0. Right? So here's this thing here. How can I make this well defined? Or it just, and the fact is, it's patently obvious that it's well defined, and I'm just asking you why it's patently obvious. What do I know about d phi? D phi is linear. Okay, so I can take this t and I can pull it out, and therefore it cancels with that t. Okay. Okay, so everybody got a fail on that, sorry. Okay, so now what I am going to do is I notice now that when t is equal to 0, okay, because that's the whole point of this is to try to get an expression for the difference quotient when t is equal to 0. So when t is equal to 0, what is this inner weak integral? So this is w integral over I. Okay, so I should say, let me write it this way. So the preceding expression at t equals 0 is weak integral over I, weak integral from 0 to 1. Oh, so sorry, that's d1 phi. This phi is a function of two variables, so I'm differentiating with respect to the first one. So it's d1 phi. of, so t is equal to 0, so it's x u, okay, dr ds. But of course, this is simply the weak integral over I d1 v of x u. Okay, because this thing is independent of r. All right, and that's what we want, right? So we want, as t goes to 0, we want this difference quotient for the integral to be equal to the integral of the derivative, and indeed it is. But I still have to show that the limit as t goes to 0 of this is equal to that. Okay, so another quiz. So why, when I take the limit as t goes to 0, um, can I conclude that this is equal to that? Okay, so remember that this is definitely equal to that. Okay, so the question is, why can I take the limit as t goes to 0 inside the integral here to go from here to here as t goes to 0? What property of the weak integral do we use to allow us to go from here to here in the limit as t goes to 0?
I mean, it's obviously some continuity
That's right.
property.
So it's continuity of the weak integral with respect to parameters here.
Yeah.
Okay, and the parameter here is t. Okay. All right, so by all right, so this is a thing that just happens again and again in this kind of analysis. Okay, so by continuity of the weak integral with respect to parameters, the limit as t goes to 0, psi of x plus tu minus psi of x over t is equal to the ds here. Oh, and I'm sorry, I'm forgetting my s inside here as well, sorry. And I also forgot it here, apologies. So there's an s argument that I'm forgetting here, sorry about that. Okay. All right, and that's the conclusion for k equals 1. Now for higher order k's, you just use the fact that when you um, uh, calculate the kth derivative, you're really calculating the first derivative of the k minus first derivative. Okay, and so the point is, since we're back just doing first derivatives again, then the calculation is exactly the same, except rather than phi inside here, you're going to have the k minus first derivative of phi with all of its arguments, right? But other than that, it's exactly the same calculation. Okay, so I'll just say the proof by induction. Okay, now reuses the above calculations or above arguments, maybe, let me say. Okay, good. All right, so another fact from your elementary analysis class that's true in this setting. All right. Okay. Right. So there's one other interesting little thing that I want to talk about. And that is, what's the relationship because um, when I write um, formulas like this, okay, um, we're always assuming here, or we're always thinking in our head that t is real. But in the definition of the derivative, t is actually not required to be real. The definition of the derivative is in a real or complex vector space, and so um, um, we sometimes want to be able to conclude things about complex derivatives by taking real derivatives, right? And we've essentially done that in this formula up here. And so let me make that formal. Okay, so relationship between C1C and C1R. And so the upshot of this discussion will be that in many arguments, you can, without loss of generality, assume that you're working in the real case. Okay. Okay. So what's the setup going to be? So U and V are complex locally convex vector spaces. Locally convex spaces. Okay. O in U, open, open, and phi, of course, from O into V. All right. So then the following are equivalent. So first of all, notice that every complex vector space is automatically a real vector space, just because real scalars are a subset of complex scalars. And so if the complex vector operations hold, then they also hold for real scalars. Okay, so that's sort of lurking in the background all the time. All right, so the first statement is that B is C1. Okay, and C1 here, if I'm telling you that these vector spaces are complex and we're thinking about them as complex vector spaces, this is C1. Okay, and I put the C here just to emphasize that we're talking about complex. Okay. All right, and then the condition to which this is equivalent is real C1. Okay, and the derivative, the first derivative, okay, is a complex linear mapping. Okay, and this is d phi at x. Okay, and this is true for every x in O. All right, so in other words, to check that something has, and I don't mean one here, I mean k. It's not very interesting when k is equal to 1. This is true for arbitrary k. Okay. So in other words, to check complex class CK, it suffices to check real class CK and that the first derivative, only the first derivative, is complex linear. Right. So this isn't hard to prove, but it's interesting because it makes us think about the difference between complex differentiability and real differentiability carefully, which we have never really done. Okay. So the first statement is easy. Um, uh, that if it's complex linear, sorry, if it's complex differentiable or complex class CK, then it's real class CK. And so I'm going to say some stuff, and then I'm going to summarize what I say with a few words. Okay. So if you think about how you compute higher order derivatives, they're always computed using difference quotients. Okay. And then if it's complex linear, then the difference quotients involve complex scalars. Okay. So if those um, the limits of those difference quotients as the denominator goes to zero exist for complex scalars, then it certainly also exists for real scalars. Okay. So certainly CKC implies CKR, just because R is a subset of C. Okay. Um, and similarly, if you have so we know here that the derivatives are complex linear because that's one of the properties we proved about derivatives is that they're linear, and that argument about linearity does not depend on whether the scalar field is R or C. And so this just follows from the definition of C1, actually. Okay, and so I'll summarize those arguments by obvious. Okay. And maybe I'll flesh that out by saying, all right, so the interesting part is the other part. Okay, so when does it, to prove complex differentiability, is it sufficient to consider real differentiability, plus this additional condition? All right, so we're going to suppose that phi is real k times continuously differentiable, and d phi of x is complex linear. All right. Okay, so the first thing we're going to do is we're going to show that not just that the first derivative is complex linear, but the higher derivatives, the dk phis, are complex multilinear. Okay, and so let's do that. So first we're going to show that dk phi, okay, so this, okay, means the real derivative. We're going to show that the real derivative is complex linear. Okay, so we've already assumed that's complex. The first derivative is complex linear, so we're going to show that that implies the higher derivatives are complex linear. Okay, so here we go. Um, um, all right, so that's what we're going to do. All right, so by um, symmetry of the derivatives, it suffices to show that the k phi, and I apologize, I keep forgetting to put the x in here, of x is C linear in the first entry. Okay, because if you know that it's complex linear in the first entry, to show, for example, that it's complex linear in the second entry, you just use symmetry to swap the first and the second entry. Then it's complex linear in the first entry. You pull the scalar out front and then you swap it back. Okay, so that's why symmetry allows you to conclude that. Okay, so this is true. k equals 1 by assumption. Okay, so assume that it's true for k equals m, and we're going to prove that it's true for k equals m plus 1, and that'll give us a proof by induction. All right, and so let x be in O and u1 up to um plus 1 in um plus 1. Okay, then we're going to calculate. All right, so we're going to calculate the m plus first derivative evaluated on these arguments. Okay, and we're going to calculate it as a difference quotient. Right, so we're going to calculate that the limit as t goes to 0, and now t is a real t, okay, because I'm assuming real differentiability, not complex differentiability. Okay, so I'm calculating the m plus first derivative, and so to calculate the m plus first derivative, I'm going to take the difference quotients of the mth derivatives. So d m phi of x, and I'm going to differentiate in the direction of plus 1. Plus 1 evaluated at u1 up to minus dm x u1 over t. Oh, and sorry, I'm trying to prove that it's complex linear in the first argument. So I'm forgetting the thing I'm trying to prove. I need to put an a in there because I'm going to pull the a out. Okay, so this is for a complex. Okay, and this is an easy argument because by the induction hypothesis, the mth derivative is linear with respect to complex scalars in its first argument, so I can pull those out in both of these terms. Okay, and so this is simply a limit as t goes to 0, dm phi of x plus m, plus 1, u1, minus dm phi of x, u1, for t, and then this is simply a d m plus 1 phi of x m plus 1. Okay, so that proves that dk phi is complex linear in its first entry for every k. Okay, and therefore by symmetry it's complex linear in every entry, and therefore it's real multilinear, and it's also linear with respect to complex scalar multiplication. So that just means it's complex multilinear. Okay. Okay, so we've proved that dk phi of x is complex multilinear. Okay, good. Now we're going to use that fact to prove the result. Okay. And so what do we need to do here? What we need to do is we need to prove that when I took this difference quotient up here, this one up here, I made sure to emphasize the t here was real because I only know that the derivative of phi, that phi is differentiable with respect to the real vector space structure. So now I need to show that it's differentiable with respect to the complex vector space structure. Okay. So what I need to show is that the derivatives can be calculated using complex difference quotients. Okay. All right. And so you're going to do this by induction, okay? Um, and for and so I'm going to just sort of skip to the inductive step rather than starting with k equals 1 and doing. I'm just going to show how this works with the inductive step. So this is proved by induction. On j going from 1 to k, okay, and the induction step is, okay, um, uh, so, um, so what I want to show is that the limit, and now I'm going to emphasize that these are complex difference quotients by writing not t, but z, okay? All right, so I'm gonna, let's say, calculate, if I know it's true for j minus 1, I'm gonna see why it's true for j. Okay, so I'm gonna take the difference quotient for the jth derivative, which is the difference quotient involving the j minus first derivatives. Okay, so x, so x plus z u j u1 up to uj minus 1 minus d j minus 1 phi of x u1 uj minus 1 over z. Okay. All right. Okay, so what should we do? We're going to do what we always do, and that is we're going to take this thing and we're going to re-express it using the mean value theorem, thinking about a curve that goes from x to x plus, so this will be a real curve, even though that's a complex scalar, it doesn't matter. I'm going to have a real curve that goes, a real straight line that goes from x to x plus z uj. Okay, so I'm going to use the mean value theorem because I know that everything works in the real case. And so, the complex structure here in this expression is only shows up through this complex multiplication. But this is just some vector. Okay, so let me rewrite that using weak integrals in the mean value theorem. All right, so the 1 over z is going to stay there. The integral from 0 to 1. Okay, and so again, so these derivatives here, these are the real derivatives, okay? And I know already from the induction hypothesis that these real derivatives can be expressed as complex difference quotients. So now I'm just going to show that that's true for j as well as j minus 1. Okay, so now I'm going to write dj, this is the mean value theorem, of x plus t, let me call it s, just not to confuse it with the t from above, s z u j u1 up to u j is 1 ds. Okay.
Yes.
All right. Oh, and as always, I forgot the derivative. Sorry about that. Z U J ds. Okay. All right. So now we do the thing we always do, and now we're going to use the fact that we showed in the first part of the proof that that this thing is complex multilinear. Because it's complex multilinear, I can pull that z out front, okay, and it cancels with that z. And, you know, limit as z goes to 0 now goes away. So it's integral from 0 to 1 dj phi of x plus s z u j u1 up to u j minus 1. Okay, and then z u j ds. Sorry, not z u j, just u j. U j s. All right, so now, again, I do the thing I always do, and that is I look at what happens at z equals 0. Okay, so at z equals 0, um, you know, this is the only place that z appears in the formula, so that's going to go away. So the integral will now be independent of s. Okay, and so this is just dj phi of x uj, oh, sorry, u1 up to uj. Again, um, um, and so sorry, I'll always do this, and so I don't mean that this is equal to that. So at z equals 0, it's equal to that. Okay. And so now, again, by continuity of the weak integral with respect to parameters, the limit, and the parameter now is z inside the integral, okay? The limit as z goes to 0 of this is equal to that, okay? So by, okay, so the limit, I'll write it all out, because it's sort of not necessarily clear what we've proved here. So if you write it out, it makes it clearer. Right, so we prove that. Now, you have to be careful here because, you know, it's not clear where R is being used and C is being used, all right? Um, these differentials here, the derivatives, are all being computed as real derivatives, okay? And the induction hypothesis is that these real derivatives here are obtained as complex difference quotients. Okay, and what this is saying, showing is that if that's true for j minus 1, then it's also true for j, because this d here is also the real jth derivative, and it's saying that the real jth derivative is obtained as a complex difference quotient. And so therefore, um, real differentiability up to order k implies also complex differentiability up to order k if you impose this extra fairly the natural condition that the first derivative be complex linear. Okay, so that's a very useful fact um, that allows you to very often prove results without loss of generality just in the real case. All right. Okay, so that seems like a good time to stop, and so I will. And today I have time to stick around for a few minutes. So if you want to stick around for a few minutes, I'll be sitting here. Otherwise, you can go, and I won't hold it against you much.